This is how intelligence is made. A new kind of factory. Generator of tokens, the building blocks of AI. Tokens have opened a new frontier. The first step into an extraordinary world, where endless possibilities are born. Tokens transform images into scientific data, charting alien atmospheres and guiding the explorers of tomorrow. They probe the Earth's depths to seek out hidden danger. They turn potential into plenty. And help us harvest our bounty. Tokens see disease before it takes hold. Cure with precision. And learn what makes us tick. Tokens connect the dots, so we can protect our most noble creatures. Tokens decode the laws of physics to move us faster. And make our days more efficient. Tokens don't just teach robots how to move, but to bring joy and comfort.
Hi, Maroka.
Hi, Anna. Are you ready to see the doctor?
What's that?
It's my enchanted tool.
Tokens help us move forward. One small step for man becomes one giant leap for mankind. So we can boldly go where no one has gone before. And here is where it all begins.
Welcome to the stage, Nvidia founder and CEO, Jensen Huang.
Hello, Paris! Bonjour! Nvidia's first GTC in Paris. This is incredible. Thank you for all the partners that are here with us. We have so many people that we work with over the years. In fact, we've been in Europe for a very long time. Even though this is my first GTC Paris, I have a lot to tell you. Nvidia, once upon a time, wanted to create a new computing platform to do things that normal computers cannot. We accelerated the CPU, created a new type of computing called accelerated computing, and one of our first applications was molecular dynamics. We've come a long way since. So many different libraries, and in fact, what makes accelerated computing special is it's not just a new processor that you compile software to. You have to reformulate how you do computing. You have to reformulate your algorithm. And it turns out to be incredibly hard for people to reformulate software and algorithms to be highly parallelized. And so we created libraries to help each market, each domain of application, become accelerated. Each one of these libraries opens up new opportunities for the developers, and it opens up new opportunities for growth for us and our ecosystem partners. Computational lithography, probably the single most important applications in semiconductor design today, runs in a factory at TSMC, Samsung, large semiconductor fabs. Before the chip is made, it runs through an inverse physics algorithm called Q-litho, computational lithography. Direct sparse solvers, algebraic multi-grid solvers. cuOpt, we just open sourced, incredibly exciting application, library. This library accelerates decision-making to optimize problems with millions of variables for millions of constraints, like traveling salespeople problems. Warp, a Pythonic framework for expressing geometry and physics solvers, really important. QDF, QML, structured databases, data frames, classical machine learning algorithms. QDF accelerates Spark, zero lines of code change. QML accelerates scikit-learn, zero lines of code change. Dynamo and cuDNN. cuDNN is probably the single most important library Nvidia has ever created. It accelerates the primitives of deep neural networks. And Dynamo is our brand new library that makes it possible to dispatch, orchestrate, distribute extremely complex inference workloads across an entire AI factory. Equivariance and QTensor, tensor contraction algorithms. Equivariance is for neural networks that obey the laws of geometry, such as proteins, molecules. Ariel and Shiona, really important framework to enable AI to run 6G. Earth-2, our simulation environment for foundation models of weather and climate models. Kilometer square, incredibly high resolution. MONAI, our framework for medical imaging, incredibly popular. Parabricks, our solver for genomics analysis, incredibly successful. cuQuantum, CUDA-Q, I'll talk about in just a second, for quantum computing, and cuPyNumeric, acceleration for NumPy and SciPy. As you could see, these are just a few of the examples of libraries. There are 400 others. Each one of them accelerates a domain of application. Each one of them opens up new opportunities. Well, one of the most exciting is CUDA-Q. CUDA-X is this suite of libraries, a library suite for accelerating applications and algorithms on top of CUDA. We now have CUDA-Q. CUDA-Q is for quantum computing, for classical quantum classical computing based on GPUs. We've been working on CUDA-Q now for several years, and today I can tell you there's an inflection point happening in quantum computing. As you know, the first physical qubit was demonstrated some nearly 30 years ago. An error correction algorithm was invented in 1995. And in 2023, almost 30 years later, the world's first logical qubit was demonstrated by Google. Now, since then, a couple of years later, the number of logical qubits, which is represented by a whole lot of physical qubits with error correction, the number of logical qubits are starting to grow. Well, just like Moore's Law would, I could totally expect 10 times more logical qubits every 5 years, 100 times more logical qubits every 10 years. Those logical qubits would become better error corrected, more robust, higher performance, more resilient, and of course, will continue to be scalable. Quantum computing is reaching an inflection point. We've been working with quantum computing companies all over the world in several different ways, but here in Europe, there's a large community. I saw Pascal last night. I saw Barcelona Supercomputing last night. It is clear now We are within reach of being able to apply quantum computing, quantum classical computing, in areas that can solve some interesting problems in the coming years. This is a really exciting time. And so we've been working with all of the supercomputing centers. It's very clear now that over the next several years, or at least the next generation of supercomputers, every single one of them will have a QPU assigned and QPU connected to GPUs. The QPU will do quantum computing, of course, and the GPUs would be used for pre-processing, for control, for error correction, which will be intensely computationally intensive, post-processing and such. Between the two architectures, just as we accelerated the CPU, now there's QPU working with the GPU to enable the next generation of computing. Well, today we're announcing that our entire quantum algorithm stack is now accelerated on Grace Blackwell 200, and the speed up is utterly incredible. We work with the quantum computing industry in several different ways. One way is using cuQuantum to simulate the qubits or simulate the algorithms that runs on top of these quantum computers, essentially using a classical computer to simulate or emulate a quantum computer. At the other extreme, extremely important is CUDA-Q, basically inventing a new CUDA that extends CUDA into quantum classical, so that applications that are developed on CUDA-Q can run before the quantum computer arrives in an emulated way, or after the quantum computer arrives in a collaborative way, a quantum classical accelerated computing approach. And so today we're announcing CUDA-Q is available for Grace Blackwell. The ecosystem here is incredibly rich. And of course, Europe is deep with science and deep with supercomputing expertise and deep with heritage in this area, and it's not surprising to see quantum computing advance here. In the next several years, we're going to see a really fantastic inflection point. So anyways, for all of the quantum computer industry that have been working on this for 3 decades now, I congratulate you for just the incredible accomplishment and the milestones today. Thank you.